here we go. Okay, a couple days ago I handed out this. So this should be in your book someplace. And we're going to move away from secants now and just take a look at functions themselves. We won't bother crossing them with lines. We're just going to look at a very typical kind of calculus type function. It's a rational function, which means basically it's a big fraction. And here's the preamble. We have seen how limits arise when trying to calculate the slope of a tangent line of a curve. Limits are also needed in all of calculus, and there are laws that govern how to calculate them. So, for our first example, we're going to look at, like I said, a rational function f of x. And the numerator of the function is a cubic, and the denominator is linear. So if I divide something that's x to the power of 2 by something that's x to the power of 1, I'm going to get something that is, or sorry, let me say that again. If I divide something that's x to the power of 3 by something that's x to the power of 1, I'm going to get something that's an x squared of some sort, right? I'm going to get some sort of parabola. Okay? In fact, here's the graph of that parabola right there. But let's say I wanted to know the limit as x approaches negative 3. Now, when I actually look at the function, when I look at the actual equation here, I should be able to tell that because x plus 3 is the denominator, that the function doesn't exist at negative 3. But just because it doesn't exist there, doesn't mean it doesn't have a limit there. It doesn't mean that there isn't a value that it's approaching, that it'll get closer and closer and closer to forever. So, let's see if we can figure out what that is. All right. Yesterday I kind of slowed down on my example and showed you how I find things with Desmos. Today, and I know I already have a video of this, but it's probably useful to just go through it once in class. Let me show you how I use Excel. So I don't really feel like punching those numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't feel like punching 12 different x values through this formula, and neither do you. That is a lot of button punching. So let's make our lives easier. And if you've never used Excel before, check this out. This is actually a fairly easy program to use. Okay, so what I'm going to do is I'm going to start by making an x column, and then I'm going to put in all the values that I'll have to plug through that formula. So negative 4, negative 3.5, negative 3.1, negative 3.01, negative 3.001, negative 3.00, oh, hang on, 01, is that right? Oh, hang on, I gotta make that column a little wider. Oh, I should have brought the mouse for this keyboard, for this laptop. There we go. There we go. And then down here now, oh, this one should have an extra 0. Let me put another 0 in there. And to change a number, just go up to the formula bar like I just did. There we go. Or you could just type right over it. And then that's it, right? Okay, so that's it. But I'm actually going to keep going. There's another side, so I'll do the other side while I'm at it. Negative 2, negative 2.5, negative 2.9, negative 2.99, negative 2.999, and then I think there's one more that actually has a fourth 9 on it. Negative 2.1234. There we go. That's all of the data that I'm going to use. That's all of the x values. And to just go back to the picture for a sec, just to make sure you all understand what we're doing. We know that we have a hole in this graph because we can't actually exist when x is negative 2. But I'd like to know what number I'd get to if I got infinitely close to x is negative 2. So I'm going to see if I can figure that out by the pattern. See, I'm approaching, did I say negative 2? I meant negative 3. Yeah, negative 3 right here. When x is negative 3, there we go. Like I was saying, I can't tell you what this function's y value is when x is negative 3, because if you plug negative 3 in for x, you end up dividing by 0, which you can't do. But I would like to know what it is as I approach negative 3. As I get closer and closer to negative 3, what number am I going to get? So rather than, I'm going to use this same method we were using in the secant lines. I'm going to get closer and closer and closer to the point when x is negative 3. And I'll even do it from two directions, starting from the left of it, -4, -3.5, all the way to -3.001. And then I'll do it from the right, -2, -2.5, -2.9, etc. But as a shortcut for punching all these numbers, I'm just going to put them through Excel. So here's how we're going to do this. Let me make that a little bigger, maybe. Okay, so for my f of x values, just put a title on this column, I'm going to have to enter a formula. And to enter formulas, you always start with an equal sign. The equal sign tells the program, oh, this is something I got to calculate. This is a formula. So I need a bracket because the numerator is going to have to divide by the denominator. So now my x here, the formula is x cubed, but I'm going to use this number. This is the first x I want to use, and this number is in cell A2. If you grew up playing Battleship, that makes total sense to you. So A2, and that's being taken to the power of 3, so that's shift 6, 3. That's how you cube something. And then plus 3 times, you use an asterisk for times. Again, I need the A2 number. And minus the A2 number. And then minus 3. Oh, and I forgot the squared. You're right. Thank you for noticing. In here, let me just get in there. I forgot my squared. There we go. So there's the numerator. Put a bracket around it. Divide is just a slash in this program. Open a bracket for the denominator, and I want the A2 number minus, no, sorry, it's plus 3. Okay, and then all you have to do is hit enter, and it'll actually take the A2 number. Notice it's gotten blue, it's highlighted. That's how you know that it's got the number you want. And it should run it through the formula when I hit enter. And it did. And now, I don't have to retype that formula. I just have to highlight, starting with that first cell, highlight all the cells I want to use this formula on, and then go over here to this weird little symbol here, fill down, and check it out. There's all of the numbers we need. Okay, so that's how I would do that. So now you've seen me do it in class. I have a video doing it. So there's something in your arsenal. If you ever get a question in this course where there's just a lot of tedious little calculations that would take you, 15 minutes to sit and plow through and hope that you don't press buttons wrong in your calculator, feel free to use Excel to kind of figure out what's going on. Okay, let's go back and actually fill them in now. So what did I notice here? What numbers was I getting? I was getting, all right, let me kind of get off of that. So I was getting 15, 11.25, 8.61, 8.60, oh, sorry, I just wrote that down wrong, 8.0601, 8.006001, and 8.00060001. And I think you can see the trend here. It seems like we're approaching 8. Just to make sure that's exactly what's happening, let's see if that's what's happening from the other side. The -2 number gave me a 3. The -2.5 gave me a 5.25. And then -2.9 gave me 7.41. And then -2.99 gives me 7.940. That's a 9. 9401. And then -2 and then 3 nines is 7.994001. And finally, the one that's 1/10,000th away from being -3 is 7.9994001. Pretty obvious that it is, again, approaching the number 8. So it's clear that as x is approaching -3, the function of x is approaching 8 from both sides. We can say then that the limit of f of x as x approaches -3 is equal to 8. And we write the limit of f of x as x approaches -3 is equal to 8. Or you can actually use the function, the limit as x approaches -3 of x cubed plus 3x squared minus x minus 3 all over x plus 3 is equal to 8. There we go. I'll give you a sec to catch up to me.
like factor that x.
Oh, you're kind of getting ahead. Yeah, you're spoiling where we're going with that.
Oh.
But yeah, I actually did give you one that we could have had something else we could have done with it, and we're going to get to that in a second. In fact, before we talk about that, we're going to talk about some rules for these things that we're looking at called limits. But we're going to come back to what you're saying. Those of you at home that probably didn't get picked up by the microphone, somebody in class here just noticed something about this function that perhaps could have made our lives easier. And if you noticed that too, good for you. We're going to talk about that in a bit. Okay, anyway, moving along here. Our general definition of a function, our general definition of a limit of a function is, come on, pen, there we go. The general definition of a limit of a function is we write the limit as x approaches a of some function f of x is equal to L and say the limit of f of x as x approaches a equals L. If we can make the values of f of x arbitrarily close to L, or as close to L as we like, by taking x to be sufficiently close to a but not equal to a. This means that when finding the limit of f of x as x approaches a, we never need to consider x equals a. In fact, sometimes you can't consider x equals a. In the last example, if we'd have let x be -3, we'd have been stuck dividing by 0, and we can't do that. So in fact, f of x does not even need to be defined when x is a. You can find the limit of a value at a function when that value doesn't even make a point that exists on the function. So, limits have properties. It is possible to find the limit using the following properties of limits, and these apply to situations where the limit exists. For example, there's the basic limit that if you are approaching a for some x, then you just say, well, then it's going to be a. Notice if you're dealing with a constant, it doesn't matter what x is, the constant doesn't change. So that's what this one's trying to tell you. And then here's, I'm not going to go through all of these. We're kind of going to maybe refer back to these as we need them. But I'll let you kind of peruse those on your own. And then let's get to an actual example. So in example 2, I would like to find the limit as x approaches 5 of x squared plus 2x minus 3. Now, oh, is this a 2? Oh, yeah, that makes sense. Okay, so make this a 2. If yours doesn't have a 2 on it, make this a 2. But it's the same function, though? Okay, thank you for pointing that out. Actually, I kind of see why they would do that. I do want this to actually fit onto the little grid that I'm going to draw here. There we go. So that's a 2. Okay. All right, so anyway, now think about this function. What is this function? What's a parabola? In fact, let's make a sketch of it, right? So if I'm looking at this parabola, I could find the vertex of it. The vertex would be x plus 1 squared minus 4. So the vertex would be -1, -4. So let's see. So -1, -1, 2, 3, 4. So there's the vertex. I could find intercepts on this one pretty easy because I notice it factors. It's x plus 3, x minus 1. So it has x-intercepts of -3 and 1. So -1, -2, -3, and 1. And there we go. So there's our parabola. Oh, I didn't draw that very good. You can draw it better than me, I'm sure. Okay, so the limit as x approaches 2. So here's 2. So I want this point right here. Now, is there any holes in this one? No. This is a continuous function. If f of x is continuous, just plug the limit value in. Right? In the last example, we couldn't just plug in -3. We would have ended up dividing by 0. But in this case, I don't have that problem. No problem. The limit as x approaches 2 of x squared plus 2x minus 3 is equal to whatever 2 squared plus 2 times 2 minus 3 is. And that looks like it's going to be 8 plus 8 minus 3, which is 5. So I guess I didn't draw this very good. This should be the point 2, 5. So 5 is my limit. As I approach from this direction and as I approach from that direction, I get infinitely close to, and eventually I get to the point 5. One thing I want you to notice is that notice that this is a limit statement. And then as soon as I decide, all right, I'm going to plug this 2 here into the formula, I don't write the limit statement anymore. Then it just becomes algebra or arithmetic. Okay, that is important. Calculus teachers and people who read calculus, they like it to be precise. They like all the symbols to make sense. So anyway, let's finish this example off. We see that if a function is, again, the word I want here is continuous, where we are evaluating the limit, the value of the limit as x approaches a is just equal to f of a. And example 3 is going to work the same way. I won't even bother drawing it this time. Right? I know it's a parabola, and I know parabolas are continuous. Parabolas don't, by their nature, have holes in them because you can't divide by a certain number or something. So I'm just going to say that this is equal to 2 times 3 squared minus 3 plus 4, which is 2 times 9 is 18 minus 3 plus 4. Somebody double check my mental math. 19. I think I did that right, eh? Yep. Okay. Let's get back to one like our first example. We cannot find that limit by substituting x equals 4 because f of 4 doesn't exist. Right? If I plug in a 4, I end up dividing by 0, and I can't do that. Remember, the definition of a limit says that we consider values of x that are close to but not equal to a. So this time, I'm going to actually take something out of my algebra toolkit. I'm going to take a look at the limit as x approaches 4 of this function. I'll call the function x squared minus 16 over x minus 4. And if I actually thought of this function as I'll call it f of x, and I tried graphing it, again, let's pretend I graphed it on Desmos, it would be a straight line, and it would have a hole at this spot here because x can't be 4. So it would actually be that graph. So that would be the graph of that function. But what do I notice about this function? Hopefully everybody notices this right away. Or not. It's early. What do you notice about it right away? Yeah, the denominator is a factor of the numerator. So I can use that piece of algebra knowledge to make my life a little easier. The limit as x approaches 4 of x plus 4, x minus 4, all over x minus 4, those things cancel. And this is going to be just like saying it's the limit as x approaches 4 of just x plus 4. So this is now a new function. These two functions here are equivalent to each other, right? So if I graph them, they're going to look pretty much the same. I'll call this one a different thing, though. I'll call this one g of x. I'll say that g of x equals x plus 4. Did I lose you somewhere? Oh, I've got this thing going the wrong way. Thank you. Let me fix that. That's right. It's got a positive slope. It should be going up. Yes, it should be going up, and it should be going, let's see. It should be going when x is 0, y. Yeah, when x is 0, y is 4. It should be going up this. Oh, I had that part right. Oh, this is it. I counted this way the wrong way. Okay, and x is 4. So it has a hole over here. So this is not the hole. The hole is 1, 2, 3, 4. The hole is right there. There we go. Okay, can you fix that diagram? Thanks for noticing that. I forgot which way slope worked. I need more coffee. Okay, so I'm going to say, maybe I'll write it over here. F of x is equivalent. Apparently I can't spell equivalent. Equivalent to g of x, right? They simplify. F of x simplifies into g of x. But that mathematically, and this is something some people have a hard time getting their head around, that doesn't mean they're identical, right? It doesn't mean they're exactly the same. A $5 bill is equivalent to 2 toonies and a loonie, right? They're both $5. But good luck if you walk up to an old parking meter with a $5 bill. Try to scrunch it up and shove it in the little slot. It's not going to work, right? These two functions are equivalent, but this one does have something different about it. It doesn't have a hole where the first one did, right? This one's going to be just fine. It does not have a hole when x is 4, right? No big fancy word that I don't know if I spelled right. No discontinuity in g of x. So there's actually one number in the whole universe that these two functions don't have exactly the same when you plug it in, and that number happens to be 4. But because they're equivalent functions, I can say that the limit of x plus 4, when I'm approaching 4, is the same as the limit for this one that was equivalent a minute ago. So now that I have an equivalent limit where I know it exists, I can just plug in the 4. And again, please notice that at this step, when I've decided, aha, I'm not going to get a divide by 0 anymore, and I'm going to plug that in, I no longer write this in the next step. I don't have to, okay? So that takes us to the answer, which is 8. Okay, and there's a little note at the bottom here. Notice we replaced the given rational function by a continuous function of x. Didn't I replace it with x plus 4? Hang on, did I copy this wrong? No, I did. This should be a plus 4 down here. Does yours say plus 4? Okay, fix that. That's a mistake. That should say plus 4. So we replaced the given function with its equivalent function when we used an algebra method to it. And the algebra method we used here was factoring. Okay? Now, if we go back to that first example, some of you probably did notice, I didn't think very many people would notice, that I could have actually used an algebra function on this one too. I could have long divided this. If you'd have taken the time, you don't have to write this down if you don't want to. If you'd have taken the time to actually long divide x plus 3 into x cubed plus 3x squared minus x minus 3, what would I have gotten? Well, x times x squared is x cubed, and then plus 3x squared, and that's not going to have a remainder. So I bring down minus x, and I bring down minus 3, and I go minus 1, makes that minus x and minus 3, and look at that. So I actually can divide this and say that it actually equals x squared minus 1, which makes sense because look at the graph. That's very definitely x squared minus 1. And the limit as x approaches, what was it approaching again? Negative 3 of the function x squared minus 1 doesn't have the same problem that this equation had, because this equation x can't be negative 3, and this equation x can be negative 3 all you like. You're going to get negative 3 squared minus 1, and that's the same thing that we got doing it kind of the hard way. So anytime we notice that we can use our algebra toolkit to make an equivalent version of the function, we do it because it's going to give us the limit that we want. So that takes us to the last example we're going to consider today. See the problem with this one? Plug in 0, what happens? You divide by 0, you're stuck. Can I factor it? Can I long divide it? No. But what else do we have in our algebra toolkit that might help us with this? Well, we have something that maybe you'd like to consider calling the property of 1. I'm going to multiply that function by 1. But here's what my 1 is going to look like. Come on, pen. My 1 is going to look like this. Do you get why that's 1, first of all? It's a number divided by itself. And what prompted me to do that? Does that look familiar to you? That's what you called rationalizing the denominator back in the day. Now, you're probably looking at it going, well, we're not rationalizing the denominator here, we're rationalizing the numerator. But at the end of the day, this is going to help. because I can kind of see what's about to happen here. When you work that out, you're going to get the limit as x approaches 0 of, okay, so multiply the top out. First times first, I'm foiling. First times first is just x plus 1. And then the middle terms, since I'm multiplying by the conjugate, they disappear. And I get negative 1 times 1, which is negative 1. And I'll leave the denominator in kind of a factored form. I won't bother multiplying it out, and you'll see why I'm not going to bother multiplying it out in a second. Maybe you can already see why there's no point in multiplying it out. What's about to happen here? 1 minus 1 cancels. So I'm going to get the limit as x approaches 0 of x over x, and then this denominator, which is the limit as x approaches 0 of 1 over. Now you might be looking at this going, oh, well, great, you just made it worse. It's more complicated than it was. Back in grade 11, they taught us that we don't like having radicals in the denominator, but I actually kind of like this radical in the denominator. Do you know why? Because x being 0 doesn't make the denominator 0 anymore. We kind of fixed it. The problem with this function originally was I couldn't plug in 0 for x. Notice I don't have that problem now. X can be 0 all day long. I'm not going to get 0 for the denominator. So that is why we did this. We did this to get an equivalent version of the function, and now I can plug in my 0. And again, once I plug in the 0, it's not a limit anymore, so don't write limit anymore. 0 plus 1 plus 1, and that's going to give me 1/2. And just to show you, we did graph these on Desmos, and the original function had a hole here, but that hole goes away and actually gets you to the value that's 1. So that is the value when x is 0, y is 1/2. So as I approach this from this way and I approach that from that way, I could go back and make a chart of values and do it the hard way again if you want. I mean, that's just so much fun, breaking out Excel just for that. But as you can see, I don't have to. I can tell from the equivalent function I graphed that the value is 1/2. So there we have it. That's today's lesson. I'm going to just stop the video for now. All right. Stop recording.